Hello. In this video, we'll be talking about the geometry of linear transformations, and we start with the following definition. A function t which maps v to w is called a linear transformation between two vector spaces v and w if it preserves both vector addition and scalar multiplication. Which means that t applied to the sum of two vectors v1 and v2 gives us the sum of images of those two vectors in the space W. And likewise, t applied to k times v1 gives us k times t of v1, the image of the vector v1 in the space W. This should hold for all vectors v1 and v2 which are in the space V. Next, we talk about important result which is valid for the Euclidean plane. So we formulate it as a theorem, and the theorem states that a function t which now maps the real plane, Euclidean plane R2 onto itself, is a linear transformation if and only if there exists a 2 by 2 matrix A such that t applied to V gives us the product of the matrix A and the vector V for all vectors V which we have in the space V. From this theorem, we have also a definition which is related to the matrix A. So the matrix A in the above theorem is called the standard matrix for the linear transformation T. And the two columns of A are: the first column is t applied to the vector 1, 0. This column vector is the first basis vector in R2. And the second column is the result of the application of t to the second basis vector in R2, which is E2. Now we discuss a few examples, and we'll be talking about the linear transformations that reflect vectors about, in case A, the x-axis, in case B, the y-axis, and in case C, the line y equals x. So those linear transformations are given by the matrices, which are respectively, for the case A, we have the matrix A1, which has the following structure. For the second example, we have matrix A2, which is defined as follows. And finally, the third matrix is given by the following expression. So if we like to illustrate those situations, then for the first example, we'll have the vector reflected about the x-axis. So say if the vector is here, then we drop the perpendicular and the reflection is here. In the second case, we have reflection about the y-axis. So now our vector, which is somewhere here, should be projected onto the y-axis and the reflection is here. And finally, when we talk about the last example, we have to sketch the line y equals x, which is the bisector of the first quadrant. And then the reflection of our vector, which we can place somewhere here, will be correspondingly after we drop the perpendicular somewhere here. Thank you very much for your attention.